Hello friends, so in this lecture we will explore the indoor-outdoor relationship and also derive a mathematical expression. The simplest and the historically most common approach that has been used to quantify the influence of outdoor air over indoor air has been the indoor to outdoor ratio of concentrations, that is I by O. Indoor air concentrations divided by the outdoor air concentrations represented as I by O. In general, for inert gases or gases which do not have any indoor source, IO is expected to be close to 1 if there is a good ventilation. Gases with indoor source such as carbon dioxide, I by O can be greater than 1 because we have an indoor source. In fact, I by O can be much more than 1. And for gases with indoor sinks, I by O can be lower than 1 because the concentration, since there is a sink, the concentrations will keep on decreasing. I by O ratios of black smoke, which is generally an outdoor pollutant, has been observed to be low when the windows are closed, because when the windows are closed there is less chance of the pollutant to come in. High I by O ratios have been achieved under well ventilated conditions because now there is more chance of the outdoor black smoke to come indoors. Generally, regression models have shown that 75% of the variation in the indoor concentrations could be explained by the variation in daily outdoor concentration. So as the daily outdoor concentration is changing, the daily indoor concentration is changing, which suggests again that outdoor air is an important source to indoor air, especially in terms of the black smoke. In some case studies, indoor outdoor relationships have been studied, for example in this work in French schools which had both the natural and mechanical ventilation. And it was found that the indoor to outdoor ratio of ozones were very low, from very close to 0 to 0.45. However, this is more profound in NOx, where the I by O ratios were 0.5 to 1, but it was also found that the correlation with building permeability was not that well. In any case, it was found that the low I by O ratios are quite related to the building air tightness, meaning if the building is more airtight, there is less chance of outdoor to indoor transfer. Therefore, the concentration of a pollutant which has no indoor source will generally be expected to be lower than the concentration which is outdoor, because due to air tightness there is less chance of the outdoor air coming in and there is no indoor source. So low indoor air concentration to outdoor air concentrations ratio will likely be observed. A few more case studies we will highlight. So in terms of the particulate matter, different particle sizes were analyzed in 17 homes in Switzerland with the natural ventilation condition. So when there was no indoor source and very low human activity, so in general no direct source and low activity, meaning low resuspension of particles. The PM10 I by O ratio was 0.7, so it is less than 1.0 because there is no particular indoor source and the natural ventilation is natural ventilation. Maybe it is not a very high exchange, or the ventilation rate is good but not very good that the indoor air is as equal to the outdoor air. So there is no indoor source, so the value is less than 1.0. But when you introduce smoking, the I by O ratio increases tremendously to 1.8. So the smoking basically has introduced the particulate matter to the indoor air at a rate which is more than how fast the deposition can take place. space. So there would be an increase in the indoor air particulate matter, and in relation to the outdoor air, the concentrations will increase much higher, and hence in this study it was observed that the I by O ratio is more than 1.8. So indoor sources will tremendously influence the I by O concentration, I by O relation. In homes where there was no apparent source, the amount of human activity was also found to contribute greatly. For example, when you have intense indoor activity, so people are moving around a lot. So when they are moving on the floor, they are maybe resuspending the dust, or if they are moving around and picking clothes, keeping clothes, some dust emissions might occur. That will increase the indoor air concentrations in relation to outdoor air. Additionally, smoking, as we have seen just now, smoking introduces a lot of pollutants, including particulate matter, and leads to much higher indoor air concentration of any given pollutant compared to the outdoor concentration of that pollutant. And in this particular work, it was found that such kind of indoor activities will increase the concentrations by up to 2.5 or more than 2.5 times. So the I by O ratio is 2.5 or more. So indoor activities, human activities generally contribute a lot to the I by O relationship or I by O ratio. The I by O ratios are generally found to be more for the finer particles due to two possibilities. Either there is a higher penetration of fine particles. So when there is a higher penetration of fine particles compared to the coarser particles, the comparison with respect to outdoor will be better for the fine particles. We will have more fine particles coming in, so the I by O ratios will be generally greater compared to the coarse particles, because the second reason is the indoor deposition of coarser particles might be taking place. Maybe they are depositing better by gravity settling in comparison to fine particles. So I by O ratios are generally greater for fine particles than coarse particles, either indicating a higher penetration for fine particles or enhanced indoor deposition of coarser particles. Very high I by O ratios greater than 2.5, as we just saw in the previous slide, have been observed when there are intense indoor activities such as human movements, smoking, or use of combustion sources such as a fireplace. Also, such combustion sources can be even kitchen activities, depending on what is being cooked. We can have more indoor air concentrations comparing to the outdoor air concentrations, and hence high I by O ratios can be observed. Then in terms of the Indian context, there when some residential homes in central India were analyzed, average I by O ratios for PM matter, PM 2.5, PM 1, PM 0.5 and PM 0.25 were close to or above 1 in roadside rural areas. So in rural areas especially, generally there is a lot of natural ventilation, so more outdoor air has a chance to come to indoor air, and in sometimes in rural area, so then when more chance of outdoor air to come to indoor air, the I by O ratio will be moving towards 1. Now in rural areas also the cooking will be such as burning of wood or use of less efficient stove, so the PM emissions will probably also be there. Therefore, it has been found that the I by O ratios will be close to or above 1 in the roadside rural areas. So the dust emitting outside is coming in, so we are moving towards 1, close to 1, and sometimes there may be indoor sources as well, so the I by O ratio can be more than 1. Sometimes the outdoor dust itself settles on the indoor floor, and then when people move around, that dust goes up and gets added to what the dust is coming from outside. The I by O ratios are generally less than 1 for urban areas. This is because the urban environment, we have more building tightness. if the building is next to roadside, there is a less likelihood that the window will be open a lot of times. So there is a less chance of outdoor air coming to indoor. And in the absence of the indoor source of PM matter, the average I by O ratio will naturally go less than 1. So in general, our indoor to outdoor ratios are dependent on the ventilation conditions and the sources. So a good management strategy of windows and the kitchen ventilators for particulate control should be decided according to the particle levels of both the indoor and the outdoor environment. If in case outdoor is much more polluted, the opening and closing of windows has to be managed. And in a general sense, a lot of people already do that. If you think there is a lot of traffic, a person will more likely keep the window closed, otherwise dust or pollution will come in, and will open if there is less activity outside. When we are using kitchen, there may be more emissions indoors, and you would like to open the window so that the emissions, the pollutants actually go out. So our management strategies of windows and kitchen ventilation depends on actually the particle levels of both indoors and the outdoor environments. So we have studied a lot about the particulates. When it comes to microorganisms, there are very few studies on airborne bacteria or fungi. In these limited studies, there was one study where the seasonal and indoor-outdoor relationship of airborne fungal spores was analyzed in 80 homes in Australia, and it was found that there was a substantial seasonal variation in spore levels in both indoor and outdoor. So depending on what season it is, we may have more spores or less spores. Compared to fungal I by O ratios, the pollen I by O ratios were very low, almost 0.025. So we have less pollen indoors compared to outdoors, almost negligible or less than 2% pollens concentration indoors as compared to outdoors. This could be because it is likely that a small fraction of pollen penetrated from outdoor to indoor environment, possibly because the pollens would have been of larger size. So they may have maybe settled down outside itself, and there was less coming inside to the indoor air. Indoor fungi levels have also been correlated with the indoor temperature, the relative humidity, and also the outdoor factors such as temperature, relative humidity, and precipitation. In one study, when indoor airborne bacterial communities in a high traffic related university building was analyzed, and the building was installed with a hybrid HVAC system, the indoor bacterial communities closely track the outdoor communities. However, the human associated bacteria genera were also more than those outdoors, because the indoor uh, there was a source of this bacteria in indoor environment itself due to the human presence. So now we can see that I by O is actually a simplified metric. All we need to do is have a concentration of outside in the outside air and a concentration in inside air. Of course, the interdependence of the indoor and outdoor air is a bit more complex, and we will try to study this using a mass balance approach. So now we will try to mathematically explore the indoor-outdoor relationship. So let us say we can divide the observed indoor air concentration in two parts. One which is originating from indoor source, let us say CIG, and one which is originated from ambient air. So this is our ambient air concentration, CAIC, ambient air. So if we are looking in this sense, we have CIN equal to CIG plus CAI. Now both are influenced by different processes. When studying indoor and outdoor relationship, we are interested in those factors that are affecting the outdoor originating component CAI in terms of influencing CIN. So what factors are leading to the relationship between Ci and indoor air and Cai, which is ambient air or outdoor air? So for this we will assume a scenario where we have certain outdoor ambient concentration Ca, a certain penetration efficiency of outdoor air pollutant indoors. So maybe if we have a fan and a filter is attached, then the penetration efficiency may be low, because if it is a particulate matter, then there will be less penetration to the indoor air. Then we will have air exchange rate, how many air changes are happening per hour. In addition, our scenario is there is some decay inside, there is some indoor source already in milligrams per hour, and then we have the volume of the space, which is in meter cube, and all these are leading to an indoor air concentrations of C in. So now how will we derive our C in? So again now we will use our concept of mass balance. So let us say we have a indoor air scenario of volume V. Now air is coming in and we have some F in. Now what will this F in be? F in would be related to the concentration which is outside multiplied by the air exchange. So air exchange would be the volume of air that is exchanged. This is going to be A times V. So concentration, air exchange, additionally this much volume is coming. Additionally we will have a penetration efficiency, because not all the particles or not all the pollutants are coming in. So we have F in, then we have a decay at rate constant K. So decay would be, let's say, reaction loss would be K times M. And there is a concentration C in. So reaction rate loss, I will make this R to be consistent with what we have done previously. So this would be K times C in times volume. Mass is equal to concentration times volume. Now we have an indoor source. So I will do this minus sign, let's say. So I'm going to do K C in times V. Then we have an indoor source. So I will add this source Q. Now we are basically trying to do dm by dt. I'm going to just write this Fn equation here. So dm by dt is Fn plus Q minus R minus F out. Now what is F out? So F out is basically the volume of air going out and the concentration of the pollutant in that air. So volume of air, okay, so F out will be volume of air that is going out would be A times V and the concentration in that air will be C in. I'm going to write this AVC in. So F in plus Q minus dk minus F out. Now we can we know dm by dt is actually V dc in by dt. So I'm going to write that also now. V dc in by dt is equal to, and I'm going to combine these things, C in and CAV. So we will have A V P C A plus Q minus V A plus K multiplied by C in. So I've used this and I've combined it here. So now if we again rewrite this equation to get an expression for C in, we will get, so we are going to bring the C in this side and this side. So we are going to get V A plus K C in is equal to AVPCA plus Q, excuse me, minus VDC in by dt. So now I can divide this all term by V A plus K and I will get is equal to A P A plus divided by A plus K times CA plus Q divided by V A plus K minus, I can discretize this, so I'm going to write this like DC in so this is the term which depends on ambient air, outdoor. This depends on the indoor strength, so indoor contribution. This term actually, or this term, this is a time variable term which goes to 0 actually when we go for steady state. as we approach steady state. So we are now interested in the term which is related to the outdoor. So if we make this go to steady state, we have a term which is related to outdoors, and that term is AP. So ventilation rate penetration factor divided by ventilation and decay multiplied by Ca, and this I can say C, which is related to ambient air. This term is defined as an infiltration factor, FINFCA, where our infiltration factor is AP upon A plus K. Now we can see that if it is a particulate matter or a fine particulate matter, probably K will be low and the infiltration factor will be governed by the value of A for a given penetration efficiency. For a highly degrading chemical, K would be high and will determine the more the infiltration factor. So we can summarize here where we have, okay, I can just use the red pen. Our solution for Cn could be Cin is equal to Pa by A plus K, Cai plus Q by V A plus K minus delta Cin by delta T A plus K. And this is the ambient outdoor originating term. This is the indoor generated term. And this is a transient term which will vanish to zero at steady state. So we can write our ambient air determined concentration as this factor, where A is the concentration in the ambient outside air and this is the concentration indoor due to the outdoor originating concentrations. And this FINF becomes our infiltration factor. In terms of particulate matter, we may be more aligned with the penetration efficiency, whereas for gaseous chemicals we may be more looking at the decay rate, and of course the air exchange rate is applying to both the terms, both particulate matter as well as the gaseous chemicals. There have been some studies on the infiltration factors. For example, here infiltration factor as a function of deposition and the crack in the building, and for this particulate range the infiltration factor is generally high. In some studies, PM 2.5 infiltration factors are around 0.26 to 0.36, black carbon around 0.28 to 0.6, ultra fines around 0.25 to 0.26. And the key indicators were the window opening behavior, which basically will affect the air exchange, same with the air conditioning. Then household characteristics, so in this case again same, what is the behavior, and also some differences due to the particle size. So different particle size may also have different infiltration factors. In general, qualitatively speaking, the building characteristics and occupant behavior will influence the infiltration factors such as the tightness of building and the window door opening and closing behavior, the air conditioning, heating, exhaust use, and also whether if infiltration devices are used, In this case, actually filtration will influence the penetrant efficiency, not necessarily infiltration factor. Then what are the particle sizes and what are the particulate matter composition? For example, the semi-volatiles actually can be lost from the particle phase due to volatilization. We will use one illustrate our calculations, that derivations that we did on the infiltration using a simple calculation. We have a single room which exchanges air with outdoor air containing particulate matter at concentration 1 microgram per meter cube. The exchange is 0.5 per hour by mechanical ventilation. Due to a installed filter, only 20% of particles are entering the room. That means the penetration efficiency is only 20%. Only 20% come in. Then, assuming a low degradation rate of 0.001 per hour, the first task is to calculate the infiltration factor. So let's do that first. So FINF we know is given by A times P by A plus K. So what is the air exchange rate? It is 0.5 per hour. So we will have A as, I can just write them here. A is 0.5 per hour. Penetration efficiency was 20%. So this is equal to 0.2 and K is equal to 0.001. So 0.001 per hour. So our F in will be 0.5 multiplied by 0.2 divided by 0.5 plus 0.001. This is equal to 0.1 divided by 0.501 equal to approximately 0.2, which is basically equal to our penetration factor. This is because the decay is very low. So that's the first part. Now the second part. The question states, what is the importance of infiltration with respect to an indoor source of 1 microgram per hour as a source of indoor source to indoor air pollution, and we have been given a room volume. So now what is our indoor source, which is F in, is equal to AVPCA. So this is equal to 0.5 multiplied by 0.2 multiplied, I'll write the volume first. So volume is 60 meter cube, 60 multiplied by P, which is 0.2 multiplied by C. Outdoor concentration is 1 microgram per meter cube. So 1. So F in is equal to 0.5 multiplied by 60 multiplied by 0.2 2. So 6. 6 microgram per hour. Then we have Q. Q is only equal to 1 microgram per hour. So in terms of the source, our infiltration, which is 1 multiplied by 0.5 multiplied by 0.2 multiplied by 60, this has a higher so this acts as a larger source to the indoor air, because we have the infiltration flux is equal to, as we saw, 6 microgram per hour, whereas Q is only 1 micrograms per hour. Okay, excuse me. So 0.5, and the units can be also determined so that we are sure there's nothing wrong in our calculation. This is meter cube, this is dimensionless, and this is microgram per meter cube. So we have microgram per hour. So we can summarize this lecture. We have explored the indoor-outdoor air quality relationship and made a derivation for the infiltration factor. Now this provides us a means to assess the relative importance of outdoor and indoor sources to the indoor air pollution.